Introduction.
Good morning, teacher.
Good morning, students. Today we learn chemical reactions of haloalkanes and haloarenes and polyhalogen compounds.
Ma'am, what are the chemical reactions?
A chemical reaction is a chemical change which forms new substances.
And what are polyhalogen compounds, ma'am?
Polyhalogen compounds are the carbon compounds that contain more than one halogen atom. Can anybody give an example?
Yes, ma'am. Chloroform is a polyhalogen compound.
Very good, Rohit. Now we learn more about chemical reactions of haloalkanes and haloarenes and polyhalogen compounds. Objectives. At the end of this lesson, you will be able to explain chemical reactions of haloalkanes, explain chemical reactions of haloarenes, describe polyhalogen compounds. Chemical reactions. The chemical reactions of haloalkanes are divided into following categories: nucleophilic substitution, elimination reactions, and reaction with metals. Nucleophilic substitution reactions. When an atom or group of atoms is replaced by a nucleophile, the reaction is called nucleophilic substitution reaction. In haloalkanes, the halogen atom is attached to the carbon atom. As the halogen atom is more electronegative than carbon, the bond between carbon and halogen is polar in nature. Due to the presence of partial positive charge on the carbon atom, the nucleophiles can attack on electron-deficient carbon, thereby resulting in the displacement of weaker nucleophile, the halide ion. Mechanism. The nucleophilic substitution reaction can proceed in two different ways. Substitution nucleophilic bimolecular SN2. A typical example of such a reaction is the hydrolysis of methyl bromide by aqueous NaOH, in which hydroxide ion replaces bromide ion. Kinetic studies show that the rate of such a reaction depends upon the concentration of both alkyl halide and hydroxide ion. That is, both the reactants are involved in the rate-determining step. According to this mechanism, the nucleophile approaches the carbon bearing a halogen group from the backside, that is, from the side directly opposite the leaving group. The hydroxide ion pushes a pair of electrons into the carbon from the backside. Bromine begins to move away with a pair of electrons which had bonded it to carbon atom. Primary halides are the most reactive, followed by secondary halides and then tertiary halides. Substitution nucleophilic unimolecular SN1. This is a stepwise mechanism in which a carbocation intermediate is formed in a slow step and then combines in a fast step with the reagent nucleophile. For example, in the first step, the polarized bond between carbon and halogen, that is bromine, undergoes slow cleavage and produces carbocation and bromide ion. In the second step, nucleophile attacks on the produced carbocation and completes the substitution reaction. The reaction follows the first-order kinetics. The order of reactivity of alkyl halides towards SN1 and SN2 reactions is as follows. Stereochemical aspects of nucleophilic substitution reactions. Plane polarized light and optical activity. solution of some organic compounds rotate the plane polarized light. Compounds with this property are termed optically active. The amount and direction of rotation can be determined with a polarimeter. If the organic compound rotates the plane polarized light to the right, that is, in the clockwise direction, it is termed as dextrorotatory or deformed and is represented by positive sign before the degree of rotation. If the organic compound rotates the plane polarized light to the left, that is, in the anti-clockwise direction, it is termed as levorotatory or L-formed and is represented by negative sign before the degree of rotation. These positive and negative isomers of an organic compound are called optical isomers, and the phenomenon is called as optical isomerism. Stereochemical aspects of nucleophilic substitution reactions. Molecular asymmetry, chirality, and enantiomers. If all the four substituents attached to carbon are different, the resulting molecule will lack symmetry. Such a molecule is called asymmetric molecule. And that carbon is called asymmetric carbon or stereocenter. Asymmetry of molecule is responsible for optical activity in such organic compounds. An object which is non-superimposable on its mirror image is said to be chiral. The property of being chiral is known as chirality. A chiral object is also called dissymmetric. For example, right and left hands are non-superimposable. Achiral objects are those objects which are superimposable on their mirror images. The stereoisomers, which are non-superimposable mirror images, are called enantiomers. They have the same physical properties such as melting point, boiling point, solubility, refractive index, etc. They have specific rotation equal in magnitude but opposite in sign. The mixture which contains equal amount of enantiomers does not show any optical rotation. As one rotates towards right and other rotates towards left, and consequently the net optical rotation is zero. This mixture is known as racemic mixture. The process of conversion of an enantiomer into racemic mixture is known as racemization. Stereochemical aspects of nucleophilic substitution reactions. Retention. If in an optically active molecule, the relative configuration of the atoms groups around a chiral center remains the same before and after the reaction is said to proceed with retention of configuration. Inversion, retention, and racemization. There are three possibilities whenever a reaction takes place with optical active compound, that is, retention, inversion, and racemization. Elimination reactions. Alkyl halides undergo beta elimination of hydrogen and halogen atom to form alkenes on being heated with KOH or KNH2. The reaction is called dehydrohalogenation. Satyrzhev rule. In most of elimination reactions, more alkylated alkene is the major product. The stability of more alkylated alkene is due to its lower energy. Hyperconjugation effect of alkyl group helps in lowering the energy of the product. Reaction with metals. Haloalkanes react with metals to form corresponding organometallic compounds. The reaction of haloalkanes with magnesium metal in anhydrous ether as solvent results in the formation of alkyl magnesium halides, which are referred more commonly as Grignard reagents. Wurtz reaction. In Wurtz reaction, two alkyl halide molecules are coupled in presence of sodium metal in anhydrous ether to form a new carbon-carbon bond and thus giving a symmetrical alkane. Reactions of haloarenes. Nucleophilic substitution. Aryl halides are very less reactive towards nucleophilic substitution reaction because resonance effect. In haloarenes, CX bond picks up partial double bond character due to resonance, which results in the fact that the cleavage of the bond in haloarenes is harder than haloalkanes, and therefore haloarenes are less reactive towards nucleophilic substitution reaction. Difference in hybridization of carbon atom in CX bond. In haloalkane, the carbon atom attached to the halogen atom is sp3 hybridized, whereas in haloarene, the carbon atom attached to the halogen atom is sp2 hybridized, due to which the bond length in haloalkane is greater than in haloarene, and it is quite difficult to break a shorter bond than longer bond. Therefore, haloarenes are less reactive than haloalkanes. Instability of phenyl cation. Due to instability of phenyl cation, haloarenes are less reactive towards nucleophilic substitution reaction. Due to the repulsion, it is difficult for electron-rich nucleophile to come closer to electron-rich arenes. Replacement by hydroxyl group. When chlorobenzene is heated with aqueous solution of NaOH at 623 Kelvin and 300 atmospheric pressure, it gives sodium phenoxide, which on subsequent acidification gives phenol. The reactivity of aryl halides towards nucleophilic substitution is enhanced by the presence of powerful electron withdrawing groups such as NO2 at ortho and para positions. The mechanism of these reactions is as follows. Ortho-nitrochlorobenzene reacts with hydroxide ion and forms ortho-nitrophenol. Para-nitrochlorobenzene reacts with hydroxide ion and forms para-nitrophenol. Meta-nitrochlorobenzene reacts with hydroxide ion and forms meta-nitrophenol. Electrophilic substitution reactions. Haloarenes will undergo electrophilic substitution reactions at ortho and para positions because electron density is maximum at ortho and para positions in resonating structures of halobenzene. For example, halogenation. When chlorobenzene solution is mixed with chlorine and then we add ferric chloride, which reacts to give 1,2-dichlorobenzene, which is a minor product, and 1,4-dichlorobenzene, which is a major product. Nitration. When chlorobenzene solution is mixed with nitric acid and then we add concentrated sulfuric acid, which reacts to give 1,chloro-2-nitrobenzene, which is a minor product, and 1,chloro-4-nitrobenzene, which is a major product. Sulfonation. When chlorobenzene solution is mixed with concentrated sulfuric acid, it reacts to give 2-chlorobenzene sulfonic acid, which is a minor product, and 4-chlorobenzene sulfonic acid, which is a major product. Friedel-Crafts reaction. When chlorobenzene solution is mixed with chloromethane and then we add some pieces of anhydrous aluminium chloride, it reacts to give 1-chloro-2-methylbenzene, which is a minor product, and 1-chloro-4-methylbenzene, which is a major product. When chlorobenzene solution is mixed with acetyl chloride and then we add some pieces of anhydrous aluminium chloride, it reacts to give 2-chloroacetophenone, which is a minor product, and 4-chloroacetophenone, which is a major product. Reaction with metals. Woods-Fittig reaction. This reaction is modification of Wood's reaction for the preparation of aromatic hydrocarbons. In a solution of bromobenzene, add some sodium, bromomethane, in the presence of dry ether, which reacts to give toluene and sodium bromide. Fittig reaction. This reaction involves the treatment of haloarene with metallic sodium in the presence of dry ether to form diphenyl. Sodium is added in the chlorobenzene solution and then we add dry ether, which reacts to form diphenyl and sodium chloride. Assessment. Before proceeding further, let us know how much you have learnt. Drag and drop the correct option. Polyhalogen compounds. Polyhalogen compounds are carbon compounds containing more than one halogen atom. Dichloromethane or methylene chloride. Due to high volatility and low inflammability, it is effectively used as a solvent, as a propellant, and as a metal cleaning and finishing solvent. The short-term effects of methylene chloride inhalation in humans consists mainly of nervous system effects, including decreased visual, auditory, and motor functions. Trichloromethane, chloroform. It is a colorless, sweetly fragranced liquid. It is used as a solvent for fats, waxes, rubber, resins, iodine, etc. It is used for the preparation of chloratone and chloropicrin. It is used in laboratory for the test of primary amines, iodides and bromides. It can be used as anesthetic, but due to harmful effects it is not used these days for this purpose. Long-term exposure to chloroform by inhalation in humans has resulted in effects on the liver, including hepatitis and jaundice, and central nervous system effects such as depression and irritability. Polyhalogen compounds. Triodomethane, iodoform. It is a yellow solid having melting point 119 degrees Celsius. It is used as antiseptic because it liberates iodine, but due to unpleasant smell, it has been replaced by other medicines. Tetrachloromethane, carbon tetrachloride. It is used in the manufacturing of refrigerants and aerosol propellants for the synthesis of chlorofluorocarbons. Carbon tetrachloride is also used in fire extinguishers and as a fumigant to kill insects in grain. Inhalation of carbon tetrachloride can cause liver cancer to humans. It can also damage nerve cells and leads to death. When tetrachloromethane is released into the air, it reaches to the atmosphere and causes depletion of ozone layer. Depletion of ozone layer results in exposure to ultraviolet rays, which leads to skin cancer, inflammatory reaction of the eye, and suppression of the immune system. Polyhalogen compounds. Prions. The chlorofluoro derivatives of methane and ethane are called freons. Some of the derivatives are CCl2F2, CCl3F. These derivatives are non-inflammable, colorless, non-toxic, low boiling liquids and stable up to 550 degrees Celsius. The most important and useful derivative is CCl2F2, which is commonly known as Freon 12. Freon 12 is prepared by treating carbon tetrachloride with antimony trifluoride in the presence of antimony pentachloride as a catalyst. In a tetrachloride solution, mix some antimony trifluoride in the presence of antimony pentachloride, and then Freon 12 is produced along with pieces of antimony trichloride. PP-dichloro-diphenyl trichloroethane. It is a white powder, insoluble in water, but soluble in oil. It is used as an insecticide. It creates pollution due to its extreme stability. It is non-biodegradable. Due to the solubility of DDT in fats or lipids, so once an animal ingests certain amount of DDT, it gets deposited and tends to stay, and it causes harmful effects to animals. Did you know? Freon was developed in the early 20th century to replace toxic gases such as ammonia, chloromethane, and sulfur dioxide used in early refrigerators. Chloroform is also used to extract and purify penicillin. Summary. Let us summarize what we have learnt. When an atom or a group of atoms is replaced by a nucleophile, the reaction is called nucleophilic substitution reaction. Solution of some organic compounds rotate the plane polarized light, and the compounds with this property are termed optically active. An object which is non-superimposable on its mirror image is said to be chiral. The property of being chiral is known as chirality. Achiral objects are those objects which are superimposable on their mirror images. Aryl halides are very less reactive towards nucleophilic substitution reaction because of resonance effect, difference in hybridization of carbon atom in CX bond, instability of phenyl cation. Polyhalogen compounds are carbon compounds containing more than one halogen atom. For example, dichloromethane, trichloromethane, triodomethane, tetrachloromethane, freons, and dichloro-diphenyl trichloroethane.